Hi, in this video, we're going to talk about using k-nearest neighbors for regression and classification supervised modeling problems. Okay, so the big idea behind k-nearest neighbors is that I'm going to look and see, hey, what are my neighbors doing? And then I'm going to do that. Okay, so let's say that we have a classification problem. Well, for k-nearest neighbors, we're going to take our data point that we need to make a prediction on. And then it's going to look around, hey, what are my neighbors, my closest, nearest data points? What are the closest data points to me in the training data? What do they have? And then I'm going to say, hey, well, the majority have this classification level, therefore I'm going to predict that. All right. For regression, what we're going to do is same idea. I'm going to take the one data point that I need to make a prediction on. I'm going to look around all the training data that's closest to that data point by our distance metric, and whatever their target variable values are, we're going to take the average, and that is how we're going to do k nearest neighbors. All right, now this is kind of an interesting model in that our modeling structure is like we just need to store the data. We don't, our training data, we don't need to have any mathematical equations under the hood. We don't save support vector machines or anything like that. We just kind of implement, hey, what's closest, what's the average, or what's the plurality, what's the voting system for what the class level should be. And so this is interesting. I've never personally seen this be my top model. I've seen it be competitive, a few times. Honestly, when I'm doing my modeling, this typically lands somewhere like in the middle, and like not as solid on train validation test split statistics as random forest, gradient boosting, but better than like a single decision tree. And honestly, it just kind of ends up somewhere in the middle typically. But it's got an interesting structure to it, and it's pretty simple because hey, we just take a couple of data points, look at that are close to what we're interested in predicting, and say, hey, what is the value here in this neighborhood? Then boom, that's what we get. All right, so we can handle classification and regression tasks. Classification is going to be done kind of like by a voting system. So if I have, like 5 nearest neighbors and we're doing binary, well, one of the two levels is going to be more common than the other. Among those 5, we're going to pick that one. For regression, we're going to take the average of those 5 observations. So when we do this, we're going to take the k most similar instances as neighbors from the training data set. So we're going to take the k nearest neighbor. So k, the default k is 5 in scikit-learn. And so the default setting is that we're going to take the 5 closest data points to the one we want to make a prediction on, and we're taking the closest data points within the training data. All right, so unlike other algorithms, other modeling approaches, this does not produce an actual model. Instead, it memorizes the training data set, and predictions are made on the fly based off of the nearest neighbors. Okay, so let's talk about the algorithm. All right, so first thing I need to do, I need to pick the number of neighbors. The 2 most important things for k-nearest neighbors algorithm is number of neighbors and what distance metric we're going to use, how we are going to define distance. So we're going to need to first determine number of neighbors, k. Then for a new observation, we're going to calculate the distance between the observation and every other instance in the training data sets. And then we're going to find the closest k of them. And then for classification, we're going to take the mode of the nearest neighbors on the target variable. And for regression, we're going to take the average of the target variable among the nearest neighbors. All right, so once again, the two major things I have to decide, there are other parameters, but the 2 biggest ones are distance metric and the value of k. And we can always explore these using like a grid search approach. Some common metrics are the Euclidean distance, Manhattan distance, Minkowski distance, and there are others. Any distance metric that's appropriate for our data could be used. All right, so some things to think about when we're choosing our distance metric. All right, first of all, nature of the data. Continuous variables are often aligned well with Euclidean or Manhattan distances. For categorical data, Hamming or categorical specific distances might be better to use. So if I know that I have all categorical data or all numeric data, maybe I want to use one of those. Remember, if I'm using scikit-learn, I have to convert everything over to numerics as typically one-hot encoding dummy variables before we run this. I still want to use the categorical metrics if all my data is categorical. Now, feature scaling. This is super important. Distance metrics like Euclidean are sensitive to the scale of the data. So we want to ensure features are normalized or standardized before applying such metrics. So this is super, super important. That how it's going to work out is that in k-nearest neighbors, my predictor variables with more variance, more spread, are going to have more influence than the ones that have less variance on them. So what we want to do most of the time, unless I have a really good reason to, I want to make sure that everything's either on the same scale or have norm 1, or subtract the mean, divide by standard deviation, something like that. I personally prefer the standardization of subtract the mean, divide by standard deviation. Honestly, it's more important to just do something like this than to have a particular method that you prefer. Also, correlations. If I have highly correlated predictor variables, I mean, really, they're redundant. And because of that redundancy, it's going to work out that, like the ones that are redundant, let's say I've got 5 predictor variables, but really, if I look at the correlations, this really should be accounted for as just 2. Well, then they've got more influence on the distance than they really should. And so that's going to degrade my model performance. So we want to deal with, correlated collinear predictor variables and get rid of those. Also, the distribution of the data needs to be taken care of. So first and foremost, k-nearest neighbor is sensitive to the scale of the data. Typically, we're going to subtract the mean, divide by standard deviation, so that we have mean 0, variance 1 for our training data, and then we're going to go through and do our k-nearest neighbor modeling. This sets it up that every predictor variable initially has as much influence as every other predictor variable. Also, we're talking about distance matrices. A distance matrix, if I take, any two, if I'm going to go through, I'm going to compute every pair of observations, that's going to be n choose 2, which is, n factorial times n minus 1 factorial divided by 2. Basically, I've got 2 factorials going on, and division by 2. Practically speaking, it's just a lot of computations to be going through. So k-nearest neighbors can be computationally expensive. And so for this fact, we want to consider dimension reduction, such as principal component analysis. All right, so I went through and I just copied and pasted help documentation on some of the distance metrics that are available to us when we're using scikit-learn. And so Euclidean distance, that is the classic distance of, square the difference, add up all those differences, take the square root. Manhattan is also called the L1 distance, is that I'm going to take the absolute value of differences between predictor variables, add them all up, and that's going to be my Manhattan distance. And we can go through each of these. We got Chebyshev, so maximum absolute difference on that one. Minkowski is a generalization of Euclidean and Manhattan distances. And so Minkowski, if I had a parameter of 3, what would happen is that I would be taking the cube of absolute values of difference between predictor variables, and then add those up, take the cubed root. And so I can do any potential power that I want with Minkowski's. Now, we also have a weighted version of that. We have standardized Euclidean. We have I always have trouble saying this. Mahalanobis takes into account correlation. Hamming, I personally have not used this on like a spreadsheet problem. Every time I've used Hamming distance, it's been for text, honestly. So I don't know too much about that. The Canberra distance is a modification of a Manhattan distance. And we can go through and see the other ones. Cosine, I've only used cosine in terms of text distances. I've never used them here for this type of problem. But according to the help documentation, potentially I could use it. All right, so here I've got the Euclidean distance presented, just because that is by far the most common to us. If you want to see the other ones, I'd be happy to produce it. But what we're going to do is when I have two data points, I'm going to go through each one of their predictor variable values. I'm going to subtract for each predictor variable. I'm going to square that difference. Then I'm going to add them all up. And so if I have 10 predictor variables, I'm going to subtract 10 times. Each of those subtractions get squared, so that's positive, add them up, and then I'm going to take the square root. Minkowski's, what's going to happen is that I can change the 2 to any other power. We're going to have an absolute value here, and then it'll be if I have a p here, it'll be the pth root instead of a square root here. Now, for feature selection, this is super important for k-nearest neighbors. First and foremost, we want to get rid of redundant predictor variables. What's going to end up happening is that redundant predictor variables are going to drown out other predictor variables. Now, this is very hyperbolic, very extreme, but imagine a situation that arbitrarily, I'm going to take one predictor variable column, and I'm going to copy and paste that 1,000,000 times. So now I have an additional 1,000,000 columns onto my predictor variables. All right, now they're all repeats of each other. They're really not adding any value because it's just a copy and paste. But imagine I made that mistake. Now, when I go through and compute my distances, effectively, because I've got 1,000,000 plus 1 representations of the same column, while I have just a handful of other predictor variables, that 1,000,001 is going to absolutely drown out the other predictor variables. And so this is an extreme way of thinking about it, but this is just to show you that redundant predictor variables will drown out other predictor variables. And so first and foremost, if I have highly correlated predictor variables, I don't need them. I don't need the redundancy. Get them out. Also, we want to remove junk predictor variables. So if I have a junk predictor variable, it's going to influence that distance calculation guaranteed, no matter what happens. Well, if it's influencing the distance calculation, but it's not providing informative value, then it's not supporting performance. That means it's going to more than likely make the model weaker, make it worse. I want to get rid of junk predictor variables. So we want to go through and we want to get rid of predictor variables that aren't supporting our project. Now, another one is that this is computationally expensive to be able to go through all the pairs of rows of data I have in my training data set. And so because of this, I want to consider going through and doing dimension reduction. Dimension reduction will improve the computation time by quite a bit. And sometimes it'll actually improve model performance if the dimension reduction effectively minimizes predictor variables that aren't supporting the computations. All right, so let's go ahead and implement this in scikit-learn. And so I'm going to first load the data using pandas. I'm taking it from UC Irvine's machine learning database. It's the heart disease data set from Cleveland. And so here I've got my predictor variables. Now, something about this is that these predictor variables are all categorical. Okay, so these are actually binary. They've got 2 levels and they're coded as 0s and 1s. I'm going to leave those alone. I'm not going to do anything with them. But these are categorical predictor variables coded as integers. I don't want to leave them as is. So I'm going to go ahead and convert those over. And here I have my numeric predictor variables. All right, now if I look at this, notice that like CP, that is a categorical predictor variable, but it's, we can see the integer values. It's coded as integers. It's coded as numeric, even though it's not. All right, now if we look at our target variable, it has multiple levels. Let's see if I can find that real quick. our targets, we can see that we have a minimum value of 0, we have a 75th percentile of 2, and maximum value of 4. So this is saying multiple classifications of heart disease. In general, when I do a classification problem, the more levels I have, the less accurate I should expect my model to be. Why? Because there's more opportunities to make a mistake. If I can, for the purpose of modeling, if I can bend my target variables to have fewer levels, and I do things sensibly, I can usually get a better model overall. And so I'm going to go ahead and convert over to just a 1 if there's any heart disease and 0 if there's not. And so what this does, this converts over to Boolean of if it's 0, it's 0, or if it's 0, it's false. If it is not 0, then it's true. And then adding the 1 converts the Boolean true false to zeros and ones. I'm going to partition my data into train, validation, and test. So I've got 2 holdout sets. And I'm just doing it randomly. Now, there are missing values in this data set. CA and thal have missing values, so I'm just putting in the mode on each of these. All right, so the binary columns, I'm not going to do anything with. I'm just going to leave them as binary. And then, but the categorical ones, I'm going to code as dummy variables. And then, actually, this is wrong. I'm deleting that. I copied and pasted that from a tree model. All right, so now I've got my categorical data, and here it is before I do dummy variables. I'm going to convert it over to dummy variables, and you can see that these are going to have multiple representations. You can see that we have, we've got all of these going on as dummy variables, 0 and 1 for each of the different levels. Now, K-nearest neighbor is sensitive to the skewness of our predictor variables. And since it's sensitive, what I'm going to do is I'm going to use a power transformer to address this. Now, I could go through and do this manually. I could do a log transform. I could do a square root transform. Here, I'm choosing to use Yo-Johnson. Just off the bat, I find it's a good choice to go with, that I'm going to let scikit-learn choose what is the best transformation for me, and I'm just going to leave it alone. I could change the parameters and use boxcox, assuming that I don't have any zeros or negative values. But the default is Yo-Johnson, which will accept some zeros, some negative values. So I like to just drop it in and go with it, not fuss with the rest. Now, K-nearest neighbor is sensitive to the skewness of our predictor variables, and even more so, more importantly, K-nearest neighbor is sensitive to the spread of the columns. Predictor variables with more spread will have more influence on the model, because if I'm trying to minimize a distance, I'm going to, when we pick our neighbors, if one predictor variable has super long spread, to get the closest one, it might be that we just go through and effectively choose the closest neighbors by that one predictor variable by itself, instead of considering the whole data set. And so it's possible, if I have a very, very large variance column, it can drown out the other predictor variables. And so I'm going to use standard scalar on this. And what this does, this subtracts the mean and divides by its standard deviation. Now, power transform also does this, but I found that sometimes every single time I've worked with it, it does a good job of giving me 0 as the average, but the standard deviation being 1 is not always 100% consistent. So I'm going to go ahead and just manually put it in here just to make sure that I have everything on the same scale. When Power Transformer has not given me standard deviation of 1, it's always been, everything's been like between 0.2 and like 1.2. And so there's like a range of values. Things are relatively close to each other, but there's no reason not to just do this extra step. All right, so I'm going to go through, and to show you just how it performs, I'm going to choose the number of neighbors to be from 0 to 30. The default is 5. And so a good range, if you don't know for this situation, if I want to do like a grid search, a good place to start would be a low value of half the default, a high value of double the default. So let's say, 2 or 3, 5, and 10 would be good starting values. This is pretty fast, pretty quick. So I'm going to go ahead and do all of these on this. What's going to end up happening is that if I have too few neighbors involved, like 1 or 2, then what's going to end up happening is that my model is going to be very sensitive to fluctuations and randomness and variability that isn't true across the whole data set. And so what's going to end up happening is that it's kind of like an average with too few values for us to trust the average. So we don't want too few in our neighbors, but also we don't want too many. Imagine the situation where I went in the opposite direction. If I set the number of neighbors equal to the number of data points in my training data, then it's just going to be the overall average or the overall most frequent level in the classification problem. And so there I'm going too far and using too many neighbors. So we want something in between. We want to find a balance. I don't want too few because we're too sensitive to noise, but I don't want too many because I'm just muting out signal and just reducing everything down to an unsatisfactory average. All right, so I'm going to run through a few metrics. These are just some ones that we can use: a Minkowski, city block, cosine, Euclidean, L1, L2, Manhattan, and a missing value, the Euclidean. There's redundancy here. City block and Manhattan are pretty similar to each other. L1 and Manhattan is similar. Euclidean and L2 are similar. So there's redundancy here. But I just want to show you like values that we can try. All right, and so how I'm going to do this is that I'm going to create a data frame where I have the nearest neighbor value, I have a metric, and then I'm going to have a column of the model structure and a column of the actual fitted values. And so this is something nice about Pandas is I can set up a Pandas data frame that actually has models on it as I go through and I do my parameter tuning. Then after I have everything set up off of this, notice I'm using list comprehension to do this really fast, really easy. This is pretty clean. One shot, I get the entire data frame together for me. And and then I'm going to go through, I'm going to fit on my training data. And so I get the results here. Now I'm going to go through and do my predictions on each of these. And so on every single observation that I have, I'm going to do a prediction. Now, some of my observations are in my training data, some are in the validation data, and some are in the test data. On this step, I'm just going to do predictions across the board because my training statistic and my test statistic, if they're far apart, that's a signal that I have overfitting. If my training statistic and my validation statistic are far apart, that's a signal that I have overfitting. So I always want to compute on my training statistic, and I want to compute my holdout statistic also. And so here we can get our predicted values. Now, k-nearest neighbor, some versions of scikit-learn have predict proba on there. The one that's on my machine doesn't. One version I saw, you actually have to go in and do a little bit of fussing to work with to get predict proba. Predict proba is not in the version that is currently on my machine. The help documentation says that predict proba to get the modeled probability values is available, but it's not on mine, so I'm just rolling with it. Just keep on going. So I'm doing predict instead of getting the modeled probabilities. Now, I always prefer to use AUC most of the time. I could have also used accuracy, or I could have used balance accuracy, F1, whichever metric works for your project, go ahead and use. And I'm going to go through and for each model, training, validation, and test, so for each model 3 times, I'm going to compute the AUC. And I'm going to do that on the training data, the validation data, and the test data. All right, and then I went ahead and sorted the values by test, validation, and train. Okay, so first thing I want you to notice is that it looks like I've got a little bit of overfitting. There's a little bit of a gap between train and test, on the first few rows of this. And so I believe I have overfit, and you'll notice that these have fewer neighbors are being used. All right, so I've only got 3 neighbors and I've got some overfitting going on. Now, if I go to the bottom, this is where I have the best test set. And so now I've got an AUC of 0.78. And here my train AUC is 0.75. All right, so it actually did better on the test set than on the training data. So when the training data, the training statistic is better than the test statistic by by a significant amount, then that's an indication of overfitting. I'm not worried about overfitting on these bottom rows. Also, notice I've got cosine as coming up as the best one on the bottom. Okay. So we got 10, 9, and 13. So in this range, I would probably pick 10 and cosine because 10 is in the middle of 9 and 13. All right, so now let's go ahead and visualize it. And so here, I'm just going through and I'm showing, just on the test statistic, I'm showing you the AUC for each of the k nearest neighbors values across each of the metrics. And so, this is something I would do if I was going to go deeper and start scrutinizing different metrics. Because if I, let's say that maybe I don't get my best result off of a metric, but consistently I've got competitive values from that particular metric, that's the one I would want to go with. Potentially also, maybe, I've got a range of potential values or potential metrics that would work for my project. Maybe if, I'm just talking to, let's say, I'm talking to educators, and educators typically have experience with Euclidean distance and sitting down and doing the calculations. And so they would feel more comfortable with Euclidean distance. Well, I might only consider Euclidean and its offshoots because of who my stakeholders are. All right, well, K-nearest neighbors is a pretty slick, interesting way to do supervised learning. It's really neat in that we don't actually really get a model. We just kind of memorize the data and then compute, what's closest and do either an average or a plurality vote to get our actual predictions. I think it's neat. I think it's exciting. And well, that's all I've got for you. Life is short. Do math.